Hello everyone, our project title is Watershed, Projecting Watershed Vulnerability to Future Wildfires. To introduce our team, myself Soumya, we have William Horner and Larissa Harrow. So California wildfires are increasing in both intensity and frequency, and water resources are threatened. Extreme climatic conditions predict increase in wildfires to be more severe and frequent in our coming future. So in addition, population increase in 2100 is predicted to be 310 million. So with this, potential water demand also would increase. So understanding the watershed vulnerability plays a very important role. For our further analysis, we did study few literatures, and these literatures evaluate the impact of wildfires on urban watershed using simulation of climate model CAN ESM2 for RCP 8.5 scenario. So they generated burn probability map and geospatially intersected these two watershed boundaries. They even projected it for future climatic conditions for about 2060, and to understand the watershed impacts or the wildfire impacts on the watershed. This formed a framework for our research question.
Yes, so our research question was basically using the framework established in the literature to use climate models to study the impacts of wildfires on watersheds and in turn on water supply. Our study area concerns the state of California and the watersheds within it. So basically all of these watersheds are the ones included in our analysis. Some lie outside of the state boundary, but they were studied in the project nonetheless. And the data that we used in our project included data from the USDA forest faucets assessment, and this basically measures the importance of small watersheds to surface drinking water. So they gave us data as shapefiles with a detailed attribute table, and the attributes that we used from that table for our geoprocessing were mean annual water yield to know how much water each one produces and the population that each watershed serves. We also use data from CalAdapt. So they have a wildfire simulations data set, and they provide burn yearly mean data. So we use data from 2000 through 2020 to establish a baseline of that data, and then data from 2030 through 2080 to demonstrate the change in burned area against our baseline. And we select climate models for that data. So we used the RCP 4.5 and 8.5, a more conservative and a more positive outlook of emissions rates. And also we selected population growth to be business as usual, which is not really anticipating a big change.
So as far as our methods go, it's important to note that there's these watershed polygons, and we're trying to combine these rather large cell-sized rasters with these polygons. So in order to do that, the main geoprocessing tool that we used was zonal statistics as a table, and we took that table and we joined it to the original watershed boundaries in order to get the burn area change watershed maps. So the biggest stumbling block was the fact that the forest of faucets boundaries were rather small. These are HUC 12, and the underlying CalAdapt rasters, as you can see, the pixels are really, really large. So we had to dissolve the boundaries, and the data within the boundaries also had to be added together in order to get these larger boundaries that encompass way more pixels, and upon which we can actually do some really neat statistics. So we also did a site suitability analysis, taking all of the factors that were previously mentioned and combining them and weighting them roughly equal, but giving a little bit more towards the change in the fire burn area. So our results, first I want to compare, RCP 8.5, which is the track we're on now, compared with a more optimistic outlook, which is RCP 4.5, 4.5 projections. For all of these maps, all of the red or light red watersheds are ones where the burn area is expected to increase in the given decade compared with the baseline. So as we move forward in time, more and more watersheds enter the really severe category of, and the blue watersheds are the ones where the amount of area that gets burned is expected to decrease over that decade. So that's RCP 4.5. Compare that with RCP 8.5 and just how drastic it gets, how quickly it sort of spirals. For the site suitability analysis, there's the population data. Okay, there's LA and this Bay Area. Those are the really large population centers compared with the Northern California regions, which have a lot of water that is yielded. So this is the water yield data that we used in the site suitability analysis. So combining them together, we get these two maps sort of showcase this process. So we're comparing RCP 4.5 with RCP 8.5. You can see that the red watersheds are the ones that are most at risk based on their water yield and their population and the amount of wildfires that are projected to occur in the 2050s. So 8.5, there are more watersheds that are at risk, obviously, and there are more watersheds that are at greater risk. So it's important, in conclusion, that we focus on the watersheds that are at a greater risk and anticipate those needs as they arise, focusing more on Northern California and east of the Central Valley. So thank you very much for listening to this presentation. We hope you have a good night.